Hello everyone. I've made quite a few different programming tutorials for the AR4 DIY 6-axis robot over the past few years, and I thought it would be a good idea to get all of those videos combined into one video and get all the pertinent sections into chapters, so that's what we've done here. You'll notice when you watch this, some of the layouts and the screens are from previous software versions, but all the buttons and the functionality is still the same and still applicable. So check out these chapters and let me know if you have any questions. This video is on programming the AR4 robot. So at this point you have already gone through the AR4 startup video, you have your robot commissioned, and you have the AR4 software open and running. So let's start out with jogging. Up here in the upper right, this panel of buttons is for jogging the robot in joint mode. Each joint has a window that tells you the current joint position. It has a button for negative and a button for positive, and it has a slider. So if I press the negative button, the joint will move in the negative direction. If I press and hold the button, the positive button, it will jog in the opposite direction. And then there's also a slider, so you can position the slider wherever you want the joint to go. So just a little demonstration there of jogging in joint mode. Now directly below that we have the X, Y, Z, yaw, pitch, and roll buttons. These are for jogging in Cartesian. So the X plus will move the robot forward in the X direction. X minus is back. Y will take the robot side to side. And then Z will obviously take it up and down in the Z direction. And then you've got the yaw, pitch, and roll, which changes the wrist orientation in any of those directions, as you see there. Now the next set of buttons below that is, it has a T in front of the Cartesian coordinate. So this is T is for tool, for jogging in the tool coordinate frame. So that means we're jogging according to the gripper. So if I jog in TX, that means the gripper, the X side, or the horizontal face of the gripper, is going to move in the X direction. So when I move there with TX positive, you can see that the face of the gripper, the robot is going to jog up according to the face of the gripper. In the Y direction, it will move according to the side of the gripper, and move along that axis. And then the Z will basically dive the gripper in and out wherever it's pointed. And kind of demonstrate that, I'll move joint 5 a little bit here. So let's point joint 5 down, and now when we jog in the Z, you can see it's jogging according to whichever direction I've pointed my gripper. So that's the tool jogging. We also have, for jogging, we have incremental mode. So right now, everything I've shown you has been in analog mode. If I click this button, we're now in incremental mode, and it will jog according to the value in this box. So right now it's at 10. So if I'm using any of the Cartesian buttons, it will jog in increments of 10 millimeters. So if I was to jog up in the Z direction, every time I click the button, it's going to move 10 millimeters. Or forward in the X, it's going to move 10 millimeters. And if I'm using joint jog, that value is in degrees. So if I was to jog joint 1, it will move 10 degrees in incremental mode. Now you also have the speed value. Right now we're at 25%. We could run that all the way up to 100%. And then you can also change that from percent to seconds. And so that means the move would take however many seconds you had in this field here. So if I wanted the move to take 5 seconds and I taught a move, it would move according to the value that I have set here for seconds. And then you can also set millimeters per second. So that means the robot would jog in a value of millimeters per second. So if I put in 10, the robot would jog in 10 millimeters per second. And then we also have the acceleration, the deceleration, and the ramp. So this controls how quickly it accelerates to speed, how quickly it decelerates, and then how fast it ramps up to that speed. So you can play with those values there and see how those affect all of the the robot speed and jogging and running programs. For the updated Xbox controller functionality, you can use either an Xbox 360 or an Xbox One controller. You can use the factory adapter or one of the generic adapters. You just have to make sure that you press the sync button on the adapter and the controller and make sure that it's communicating through Windows. Then in the software, you can go in and press the Xbox on button, and then you can see it'll say Xbox communicating. So once that's communicating, then you can control the robot using the controller. You can see here, starts out in joint mode with the upper stick left to right, that controls joint 1. Up and down is joint 2. And then on the other stick, right to left is joint 3. And then up and down will be joint 4. And then on the D-pad, if you press up, that's joint 5. And down is joint 5 in the other direction, and then we've got joint 6 for left and right. Now to switch to Cartesian mode, you press B, and now on the left stick, if I press forward, the robot moves forward in the X direction and back in the X direction. Side to side is the Y direction, and then the other stick down and then up, that is the Z direction. And then left and right, that's going to be the rotation in the X direction, and then the D-pad up will be rotation in Z, and then rotation in Y for those buttons there. Now if we press the X button, that'll teach positions, so you can see here it's just adding positions to our program. And then when we press the Y button, that should toggle our servo gripper, and if we press the start button, that'll toggle our pneumatic gripper, so you have that control. On the trigger buttons, if you do the left trigger, that'll bring the speed down. You can see here, as I press that, the speed goes down, and then when I press the right trigger, you can see it going back up. So you can control the speed there with those. And then the A button will take us back to joint mode. So you can see here, I'm jogging in joint mode. And then the last thing is the bumper buttons. Those will jog us in the tool Z direction, so that will dive the gripper in and out of places. So the tool Z jogging is pretty useful. You can see here, anywhere I reorient joint 5 and then hit Z in and out, it will simply jog or dive the gripper in and out no matter which way I've decided to point the gripper. If I point it out here, it'll dive in when I press that button. So that's pretty useful functionality, but that's pretty much all of the control on the Xbox controller. If you wanted to create a new program, you just give it a name. We'll call this test and hit OK, and that'll create a blank program here. So then we could, for example, teach a position. Maybe we'll jog joint 1, teach another position, and jog in the Z direction, teach a third position, and then you could go to your root folder and open up this program in a text editor, or you can just hit this button for open text and it will open it up in your text editor. Then I can, for example, if I wanted that to be a linear move instead of a joint move, and if I wanted to change my X position, for example, there I could change it and then hit save, and then I can just come here and hit reload, and it will reload that file, and you can see my changes have taken effect. And you can still, edit each line individually like before with the get selected and insert functions. So next, let's just talk about building a real basic program, putting some moves and some commands into our window here. So from this drop down right here, we have the move types that we can select from. So right now I'm just going to go over a couple real basic moves. We'll talk about a joint move and a linear move and a move in the rotation of joints. So we'll just talk about those three right now, and we'll come back to the offset J as well as some of the other position register related moves in a few minutes. But a move J is just a joint move. That is a move of all the joints working together. That's not necessarily going to execute a perfectly straight line. It's just going to move to the position you've asked for using all of the joints. So right now that's what's selected. So I'm going to hit teach position, and it's going to create that move in a line here. And then let's say that we want to create another move after that. So let's move joint 1 and joint 2 and joint 3. And then we will teach another move. And so now I have 2 moves in my command window. So if I select the first one and hit forward, it will move back to that position. And you can see it's kind of a sweeping move. It's not necessarily moving the robot in a perfectly straight line. You can hit forward again and re-execute that position. Now let's say we wanted to make a linear move where the robot would move in a perfectly straight line. So let's jog the robot forward in the X direction. And then we'll change our move type to a move L for linear and place a move L in the program. So now I can go back and re-execute joint move to that position, and that's just a kind of a sweeping joint move back to that position. And now when I execute a move L, that's going to move the robot in a perfectly straight line along that path. So that's what a linear move is. And then the other move that I wanted to talk about right now is a move R. That stands for rotation, or rotation of joints. So I can select that, and when I teach a position, you can see here, rather than storing it, for example, this one stores the a linear or a joint move, shows the X, Y, Z, yaw, pitch, and roll Cartesian coordinates of the position. A joint move puts in the value for joint 1, the value for joint 2, the value for joint 3 and 4, and so on. So that would move to that position simply in the joint values for where that joint is. Now you can also modify positions and delete positions from your program window here. So if I wanted to delete a position, let's say I wanted to delete that one, I just highlight it and click delete. We'll delete that one as well. And then if we wanted to modify a position, for example, right now we have this rotation move, rotation of joints move that we've called home, and they're all at 0. Let's say, for example, that I jog joint 1, and then I can hit, as long as I'm still on move R, I can hit modify position, and it just modifies this position to have the new value that it had before. And obviously we lost we'd have to recomment it and give it a new name, but it makes it so that it doesn't have a replicate another move that has the same name in it. Another thing that you can do is call a program. So let's say, for example, we wanted to call the home program. I can type in home and hit call program, and it will call the program home. So now if I was to execute that line on call program, it moves me into the home program, and then I could execute that move to go home. And so now we're home. Now if I want this to go back to the previous program where we came from, it has to have a return at the end of it. So if I put a return at the end here and I execute that return, that will take us back to where we came from the main program. So anytime you call a program, that program that you called needs to have a return at the end of it. And you can only go one layer deep, so you would only want to call programs from this initial program that you started. If you called home and then tried to call another program from home, that would not work. It only lets you go one layer deep on that. Another thing I wanted to cover right now is the manual program entry field and how that works. So I can come select any line. So I'm going to grab that move R and I'm going to hit get selected, and now I can edit that line here. And so for example, for joint 1, let's say that I want joint 1 to be at 0. I can make that a 0. For joint 2, let's also make that a 0 value, and we'll just do that for all the joints. So now I have this in my manual program entry field box that's been changed, and I can come down here and I can either replace that line with my new line or I can insert it below. So I'll insert it below, And so now if I execute that line, that will take all of my joints to a 0 position. So this just gives you a way to, to specify a move in which joint rotation that you want. As far as the program entry field, this comes in handy. If this move, for example, let's hit get selected on that again. Another thing in here is we have a little asterisk in between the brackets there. That's simply there as a placeholder for you to give the position a name. So I could call that position home, for example, and then I could I'll hit replace and I will replace that line. So now in my code I can give my positions names so that as I go through my code I can quickly see a name that tells me what that position is. And then using the manual entry field, I can also use it to insert that line anywhere I want. So if I wanted to add my home position in multiple places in the program, if I wanted to start up here right below tab 1, I could hit insert and I could put my home position here, do some other motion, and then come back to my home position there. So that's how that entry field box there works. So next let's talk about arc moves and circle moves. Here from our move type drop down, we've got you've got move A and move C. So I want to talk about those next. So in our example here, I've just got a roll of tape on a box. So give us something to use for an example. Let's start out with I'm just going to teach a joint move that's in the position you see here that is above the roll of tape. And then we need to make a starting point for our arc. Let's start out talking about an arc. So I'm going to jog the robot down. And too far there. Let's just start there. So let's call that our starting point. So we need to teach a starting point. So I will just do a move L and teach that position. So that is our starting point of the arc. Then we need a midpoint and an end point for an arc. So I am going to jog the robot. Let's go forward in the X, and then let's come over in the Y to the edge of the roll of tape. And so we will teach that. That will be our midpoint. So we'll do an arc move, midpoint, and we'll teach that position. And then let's jog the robot forward, and then we'll come back in the Y a little bit, and we will teach that as our arc endpoint. And then we'll execute through these moves. We'll go back to our starting point that's above, and then we'll execute the start point for our arc. And then when we hit forward on the execute for the mid and the end, it will execute both of those together, and we'll execute our arc move, which goes in an arc around the tape as you see there. So now let's talk about doing a complete circle. I'm going to go ahead and delete the arc moves there, and we'll move back to our starting point. So now for a circle move, we need a center position, a start position, and then we need to know what plane that we're on to do the circle on. So let's start out with the center position. So I'm going to jog the robot, and I'm going to put the pointer in the center of that roll of tape. Okay, so let's call that our center. That's pretty close to the center of the roll of tape. So we'll teach that position. So that is our move C center, and then we need to jog to our starting point of where we want the circle to start. So I'm just going to jog straight back to the edge of the roll of tape, and I will teach that position for our starting point. And then it needs to know what plane and space that it is, because it could make this circle on any angled surface. So it just needs a third point, and that can be just any other point on the roll of tape. So I'm just going to jog to the side a little bit, and we'll just call that good for our plane, so that's on the same plane that we're on. We could teach that position. So now I will execute that position, and then when I execute the move C center, it'll execute all three of those together to run our circle. So next I want to cover a little bit of registers and position registers, as well as the offset J move type. So if we go to the registers tab, you can see here we have 16 registers. These are just single integers that are used for counting. And then we have 16 position registers, and these are values that have 6 different elements, 6 fields for the X, Y, Z, yaw, pitch, and roll of a position. So if we go to our command window here, and we taught an offset J position. If I teach that, what you can see here is we have a position that is the X, Y, Z, yaw, pitch, and roll of our current position, but it is going to be offset by whatever is in position register 1 right here. And it puts that 1 in there by default. You can use any of the position registers you want. You could, for example, hit get selected and change that to position register 2, for example. And you could insert that in your code, and you could use as many position registers as you need. For right now, I'll delete that. We'll just stick with position register 1. So if I was to execute this, nothing's going to happen because it's at its current position where I taught it, and position register 1 is all zeros. Now, for example, if I took the third element, the Z value, and changed that to 25, for example, and then went back and now re-executed that line, the robot's going to move up 25 millimeters. If I go here and put in, say, 50 and execute it, it's going to move up 50. So now let's talk about how to manipulate position registers from the code. Let's say in our program, we want to start our program right under tab number 1, which is going to be the top of our loop. Let's say that we want that position register 1 to element 3, the Z value. We want it to start at a value of 0. So we've got position register 1, element 3. Element 3 is the third element, the Z value in that position register. And we are going to set that equal to 0. So I'll come right here and I'll put that in my code. And now when I execute that line of code and we come back here, you can see that's now a 0. So now let's say that we want that position register to increment or decrement by some amount. I can take, and if I was to make that, let's say 10 millimeters, that would just statically set the value to 10 millimeters every time the line of code runs. But let's say I want it to increment by 10, I would put 2 pluses in front of it. I do plus plus 10. And so now if I put that line of code here, it will increment by 10 each time. So if I hit forward on it and come look at it, now it's got a value of 10. If I execute it again, now it's 20. And so on. So every time that runs, it's going to increment the value by that amount. And what this is, would be used for is for stacking. For example, if you had a pick routine, you go pick apart, and then you come back here, and every time you place it at this position, it's going to place, 1 height higher. So let's say we wanted to run this in a loop. We haven't talked about the tabs yet, but we have tab number 1 here. If I do jump to tab, if I'm going to put value number 1 right here, and put jump to tab 1. Now every time I execute that, it's going to jump back to the top. But then of course it's going to set that to 0, so I just screwed that up. So let's take this value and let's do get selected, and let's put it above that. So let's insert it there, and then below our tab let's delete that. So now when we start our program, at the beginning of the program it would set element 3 to 0, and then we're at tab number 1. So now if I hit play, it's going to move to this position, increment the amount, and then jump back up top. And let's also put a little wait time in there. Let's put maybe 1 second so it's not moving too quick, so we can see the pause in between each loop here. So we'll put a wait time of 1. This is in seconds. You can put any value you want in there. So let's start at the beginning and hit play and see what happens. So every time it runs, it's going to move the robot up 10 millimeters. Now it's just going to keep going until we get a join out of range error, so I'm going to hit stop right here. So that brings us to registers, for counting registers. So let's say we didn't want that to keep moving up indefinitely, we only wanted it to move up, let's say 5 or so times. We could use one of these registers to count for us. So what I could do is I could come up to the beginning of our program and I could say register 1 equals 0, and I'll put that at the top of our program, and that'll reset that register to 0 every time the program runs. And then let's say down here, after we've moved up, we want to increment register 1 by a value of 1. So I could hit ++1 there, and now every time this loop runs, that register will start incrementing and counting. But then we want a way to stop after that register gets to, say, a value of 5. So let's go right up here to the top of our loop, and at the very top of our loop we'll say that if register 1 equals 5, then let's jump to a different tab. Let's jump somewhere else, and we'll jump to tab 2, which we haven't created yet, but we will here in a second. So I will put that right here. So this will evaluate, once that gets to 5, it will jump to wherever tab 2 is. So I'm going to come down here and I'm just going to create tab 2, which will just get us to a different place and out of our loop in the program. So tab number 2 will be the end of our program. And another thing that I didn't talk about was comments. You could use this manual program entry field to put comments in your code. So let's you can put any comment you want as long as it's not a decipherable line of code. So I usually just put in some hashtags, and let's just put in a comment that just says end of program, and we will put that, we can just put that right before tab number 2, and we can just insert that right there. So that kind of tells us that that's the end of the program when it gets to tab number 2. So now if we come to the top and hit play, what's going to happen is we're going to reset all of our registers. We're going to reset register 1 to 0. We're going to reset our position register 3 to 0. Then we're going to start at the top of our loop, our tab number 1. We're going to evaluate our register 1. When it gets to 5, we're going to be done and we're going to jump out. But then we're going to start, we're going to move to position. Then we're going to increment the position register by 10. We'll wait for a second. We'll increment the register that says, yeah, we've done it one time, and then we'll jump back up to the top, and we'll just keep doing that. And when it hits this, if register 1 equals 5, it'll jump to the bottom and end. So it should only move up 5 times. Okay, so there you can see it stopped after 5 loops. It only moved 4 times, I apologize, but you can see how that worked there, that it stopped after it went through the loop 5 times. So now let's talk about the remaining position register functions down here. We've got move to position register. That is very similar to the offset J, where if I choose move to PR and hit teach, it basically the robot's just going to move to whatever value I've put in position register 1. We've also got teach position register, and what that does is just populates a position register for you. So if I hit that, that's going to add 6 lines of code that will put the current position of the robot, which you see here, each of the current positions, it's going to put those into a position register. So if I execute all of those lines and then I look at my registers, it's put our current position into position register 1. So now we have our current position. So this might be how you would teach your, say, your starting position for a stack, for stack of blocks, for example. And then the other function we have on here is to move offset of a position register. So if I select that, it's going to take whatever register I put in here, and it's going to offset it by the next one. So if I put 1, it's going to offset 1 by 2. So let's do that now. I'll come right here, and actually before we do that, let's just put in some blank comments just to give us a little space so it makes it a little more readable. And so I'm going to insert a couple of lines there, and then let's put that right there. So now what we're going to do is we're going to move offset of position register 1 by whatever's in position. We're going to move to position register 1 offset by whatever is in position register 2. So if I was to execute that right now, it's not going to do anything. It's just going to move to where it's currently at, because what it's doing is moving to this first position register offset by whatever's in position register number 2. Now if we wanted to do an example where we were going to stack and move upward and then do a second row, we would, kind of similar to the last example, let me move the camera over here out of my way a little bit. What we could do is we would say that we would take position register 1, element 3, and we will offset it by 10, increment it by 10 like we did last time. And we could place that right there. And so now when I execute that line of code, it's going to increment the value by 10. And so now when I re-execute this row, the robot's going to move up by 10. And so every time I do that, the robot moves up by another 10. Very similar to what we did in the last example. So let's do the same thing where after 5 rows we jump to a separate set of code. So up here in our first portion, let's take counting register 1 and 0 it to 0. So now at the beginning of the program, we're going to set our position, we're going to reset that register to 0, and here in our code, let's increment it, do ++1 each time. And so now we're going to move up by 10, we're going to increment our counter, and then we need to jump back up here. So let's put in create tab number 2, and let's create that up here, and this is going to be the top of our loop. So let me just put in a comment that says top of loop just to try and help keep this readable. So this is the top of our loop, tab number 2, and then let's create a jump to tab number 2. So now it's just going to keep running through this and moving up by 10 each time. But what we want to do is we want to go somewhere else once it gets to 5. So we're going to say if register 1, let's just do 6 this time. If it equals a 6, let's go to tab number 3, which we haven't created yet. Okay, so this is going to run through and loop through and climb and keep moving this register up by 10 until it gets to till register number 1 gets to 6, and then it's going to jump to tab 3. So let's come down here and create a few more rows just to give us a little bit of space. And then let's call this shift rows code. So down here is where we're going to want to shift our row to the next row. So what we can do is, since we're moving to position register 1 offset by what's in 2, we want to take position register 2 and we want to take the Y value, element 2, and let's say we want to increment it by 25. So each time we get to this shift rows code, we're going to shift over by 1 row. It's 25. Now we also want to make sure that our height goes back down to the table, to the starting point, so we can come grab this line, which is our position register 1 element 3, which we've been incrementing by 10, we want to set that back to where it's at. So I'm going to hit get selected, and then I'm going to insert it right below that line right there. So now we've started at the bottom layer again, but we've moved to the side by 25 millimeters. And then the other thing that I want to do is I want to take register 1 and make it equal to 0 the same way we did up here. So I can come here and say position register 1, or not, excuse me, register 1 equal to 0. I can place that here. So now when I get to this shift rows, I'm going to shift to the side by 25. I'm going to reset my Z height. I'm going to reset my counting register, and then I want to jump back up to the top of my loop, which is tab number 2. So I'm going to do a jump to tab number 2. So now when I run this code, it should do a stack of 5, move to the right, do another stack of 5, move to the right, and keep. And there's one thing I forgot to do here. Our shift rows code, I forgot to put a tab here to jump to, because when we get to 6 high, we want to jump to tab 3, and I totally forgot to put a tab 3 there. So let's create tab number 3 and put it right there. So now our shift rows code actually has a tab to go to. So now if we come to the top and play this code, it should do a row 5 tall, come down here, shift to the right, reset everything, come back up, and do a stack of 5 again. So let's see how that works. So you can see each time it gets to that shift rows code, it moves over by 1. So now we've done 3 stacks, and now we're moving to a 4th stack. So it kind of gives you a little bit of an idea of how you can use these position registers to manipulate position, and you could keep moving to the side, you could move front to back, however you need to manipulate the position registers. In this section we have our joint calibration. We have the auto calibrate button, which will auto calibrate the robot, which we covered in the startup video. These checkboxes, you can select which joints you want to be in the auto calibration. Typically you would have all 6 joints selected, but if, for example, you had a large end of arm tool that would hit the arm when calibrating, you could deselect 5 and 6, for example. Anything on this screen, if you've made a change, you need to hit save for it to take effect. And so now if I hit auto calibrate with 5 and 6 deselected, you can see it will run the auto calibration, but you can see axis 5 and 6 aren't moving, so that you could do the auto calibration for joints 1 through 4 and then come back and do joints 5 and 6 separately. So the auto calibration completed, but then if I wanted to do joints 5 or 6 separately, I could click calibrate joint 5, and it would just do 5 on its own. And then you can see here on the config setting tab in the software, this set of checkboxes right here is for stage 1 of the calibration, and this set of checkboxes here is for stage 2. So I have it set that stage 1 will calibrate joints 1, 2, and 3, and stage 2 will do 4, 5, and 6. And then another update on this version is that I've added the external axes, axis 7, 8, and 9. So if you had a travel track or a turntable or some other axis that the robot is controlling, you can also now include its calibration. So if I checked joint 7 for a travel track, for example, to be in stage 1, it'll now calibrate the track during that portion of the calibration procedure, and then you just hit the auto calibrate button to start the procedure. If you find that you have variation in one of your limit switches, we now have a procedure for fine-tuning the calibration. For example, if you put a digital level on axis 3, for example, and find it's off by 0.3, you can go into the software on the calibration tab and put in minus 0.3, and then just click calibrate single axis for joint 3, and you can see it'll recalibrate that joint, and then that fine-tuning value has brought it right back to a perfect 0 again. You can see here I'm on the main controls tab, and I've added this line here, this section on the if-then functionality, so it makes it a little more streamlined and easier to use. I've got an overlay here of the robot, so you can see a little video screen of what the robot is doing. This if-then functionality allows the robot to react based to different inputs, so we can react to an actual physical input on our board. We can react to if a register value changes, or we can react to if an external comm device sends a signal. And then from there, we can choose what those inputs are and then decide if we want to call a program or jump to another section of the program. So we'll start out with a quick example showing an input. You can see here I've got our gripper control enclosure here. This has the solenoid valve, the relay, and an Arduino Nano board. And the software is connected to this Nano board and monitoring all of its inputs and outputs. And you can see here I have a switch wired from the ground terminal over to input number 2, so that when I press the switch, it's going to force that input down to 0. The Arduino boards are very susceptible to floating voltage, so you either need to wire them to ground so that when you press the switch it gives it a ground signal, or you need to wire it with a 3-way switch, but I have a tutorial on that on the tutorials page on the website. So to start out with, let's set this to be input 2, which we have our switch wired to, so I'll put a 2 right there, and then if that switch is pressed it'll connect it to ground, so that'll be a 0 in that field there. And then let's say that when that happens we want to call a program, so let's say we want it to call the home program, so I'll just put home in that field there. Now over here I've got a little test program set up, so if I hit play on this, it just has the robot moving up and down. So you know, maybe this represents the robot doing some activity, picking and placing or something like that. So let's say when that button is pressed, I want the robot to stop what it's doing and go home. So I'll just put the cursor right here and I'll hit insert if command. And so now when I hit play, the robot will move up and down, and then every time it passes through this if-then statement, it will evaluate whether or not that button is pressed. So you can see if I press and hold down the button, when it gets to that line of code, it's going to go to the home program and run the robot home. So you can see it ends here in the home program, but let's say that I wanted it to return back to what it was doing after it goes home. I can come right here and put in a return on this, and now let's reload our test program and start it again. And if we hit play on it, it will go back and continue doing those 2 moves that represent the robot doing some kind of work. And then when I press and hold the button, it's going to go to the home program. It'll run the robot home, but then when it hits the return, it'll come back to where it came from and then keep doing those movements again and return to what it was doing. So now let's say instead of calling another program, we wanted it to jump to a different line of code. So we'll do a real quick example on that. So I'm just going to come here and delete that line that we put in, and then I'm going to come down here below tab 1 and we'll just put in some hashtags for a comment. So we'll just insert a comment to give us a little bit of space, and then down here let's create a new tab to jump to. We'll call that tab number 2, and we'll hit create tab. So now I have a new tab to jump to. So let's say instead of calling a program, we wanted to jump to tab, and we want it to jump to tab number 2. And so now we can come back up here, insert that command again, and now it says if input 2 is 0, it'll jump to tab 2. So now when we press play on the program, it's going to continue running those 2 moves like before, but now when I press and hold the button, when it gets to that line, it's going to jump down to tab 2, as you saw there, and stop at the end of the program, so you could have some more code down here to do something different. Okay, so now let's do an example using the if-then functionality, but monitoring a register, making the robot react to a register value. So we'll go back to our example program here. I'm going to go ahead and delete that line that we put in, and then I'll delete these other lines here that we put in. So now we're kind of back to our original example program. So if we're dealing with registers, we can use registers for a lot of things, and in this example we use it for counting number of cycles. So I'm going to take, and let's say register 1. We want register 1 to equal 0, and I'm going to put that at the very beginning of our program above the tab that we're jumping to, so that initializes our register. So when we first start the program, it's always going to set it to 0. And then let's say every time it completes its cycle of movements, whatever action it's performing there, we want it to count, and we want the register to increase. So then we'll just take this field, instead of making equal to 0, we'll do a ++1, and that will make it increment each time. So we'll put that in our code. So now when I come here to the top and I press play, it's going to start doing these two movements, and every time it runs through this, it's going to increment the register for us. So if we go to our registers tab and we look at register 1 up here, you can see how it's incrementing every single time the robot goes through a cycle. So it's basically counting cycles for us there. So we'll go back to the main tab and I'll hit stop. And so now what we want to do is we want to make it so that if register 1, let's say that it does 5 cycles, when it gets to 5, that then we want it to call program home. So we want it to go home after doing something 5 times. And so I will put that right here under tab number 1, and we'll insert that command there. So now if we step through this program, I'll hit forward, and I've just executed that row register 1 equals 0. So we go back to our registers, we can see it zeroed it. And so now when we hit play, it's going to run through this 5 times, and after the 5th time it should go back home. And so there, after the 5th cycle, it jumped to the home program. And that will work the same way if you wanted to call a program or jump to tab. It's basically just looking at that register, and when that register equals the value that you set it to, it'll perform or jump to a tab or go home. So you can also do wait times. You can wait for an input signal, so you can wait for a coil or input to be equal to a certain value and then have a timeout after a certain amount of time. Or you can set your 5-volt output on your Arduino board, or you can set a coil or a register value equal to whatever you need it to be and have the robot set those anywhere in the program. I've added this whole section for reading from a PLC for a Modbus device. So just to show you that, I'll put in the device address that I'm working with right now is device number 7. And so if I want to read the first input, that's Modbus address 2048. So I could read that input, for example, and you can see it's currently at 0. And if we look at the software, we're talking to Direct Logic DL06, and you can see that the first input is off. And then if I toggle the switch that I have connected to that input and turn that on, then we can go back to the software and read that input, and you can see it changes to a 1, so it's reading that value. And then, for example, reading holding registers, if I wanted to read the holding register at location 1088, and then put in that we want to read 1 register and read that holding register, you can see its value is 0. If we go to the software, the octal address for that same 1088 is 2100, and you can see it's reading 0. So if I was to change that to say 123 and write that into that holding register, we can go back to the software, read in that holding register, and you can see it reads that in there. And you can see we can also read in coil addresses, we can read in input registers, or we can write to a coil or write to a register. So now if I wanted to use a PLC signal in a program to have the robot be able to react or control something in the PLC, you can see here we have command lines for putting in statements, for if statements, for wait statements, or for setting device addresses. So for example, if I wanted to create an if statement, I can do that based on a 5-volt input or a register, counting register value in the software, or a COM device. But now we have these different Modbus choices here. So I could choose input, Modbus input, and then choose address. Again, we'll do 2048 for input 1, and we'll say when that value is equal to 1, we want to do something. So we can either call a program, jump to a spot in the program, or stop the program. So we'll leave that at call program, and we'll just call the program home. So I'm going to load a program here. I'm going to load test, and you can see I've already put that line of code in here already. So I could come in here and hit play, and the cursor will just keep running through this program. And when I flip that button for that input, you can see I've turned it on, and now it jumps to the home program, and now the robot is running home based on that input. So you can also do wait times. You can wait for an input signal, so you can wait for a coil or input to be equal to a certain value and then have a timeout after a certain amount of time. or you can set, you know, your 5-volt output on your Arduino board, or you can set a coil or a register value equal to whatever you need it to be, and have the robot, you know, set those anywhere in the program. So I want to cover two different types of grippers that you can put on the robot. We're going to talk about pneumatic grippers, and then we're going to talk about servo grippers. So the pneumatic gripper, this is what I would recommend. I like the pneumatic gripper. It has a lot more strength for lifting components, and the speed is a lot faster. So if you wanted to you know, grab parts quickly or lift up a heavier load, I would definitely go with a pneumatic gripper. And there's a few components you'll need, you know, that we'll talk through here. First of all, we have the Arduino Nano board. We've got a relay, we've got a 5-way solenoid valve, and then we've got the gripper, and then we've got an air source. So I get quite a few questions on the air source. All I have here is just a 3-gallon air compressor that I got from Harbor Freight Tools. It's fairly inexpensive. And then the outlet, the quick disconnect from the compressor, I just have that an adapter with a push connect fitting to 1/4-inch pneumatic air line, you can see here. And then on the solenoid valve, I have another push connect 1/4-inch going to the center port on the bottom of the valve, as you see there. So we'll talk more about the valve in a minute. I wanted to talk about the Arduino and the relay board. The reason that we have an extra board in the architecture here, this Arduino Nano, is that the Teensy operates at 3.3 volts. So we're just using the Teensy board to control the robot. Now, we could use a few of the extra pins of the Teensy to control 3.3 volt devices, and I'll talk about that later. But for the most part, most devices and relays out there, most servo grippers and relays are all 5 volts, and I found all the 5-volt relays to be much more reliable than the 3.3. So I've added the Arduino Nano as a device to control and monitor peripheral devices. So if we open up the manual, let me pull that out of the way there. If we open up the manual, on page 240 is where we go over wiring the Arduino Nano to the relay board. You can see right here at the top, this is where we're wiring the 5 volts to the relay, so the powers the relay board. And then right here on output 8 is the first output that we've allocated. 8 through 13 are the pins that I've allocated in the software to control outputs. So you can see that we have that connected to the input on the relay board right there. So those are the connections from the Arduino to the relay board. And then the next thing that we need to connect from the relay, as you can see here, I have connected, you can see this black wire here. That black wire goes from the negative terminal on my 24-volt power supply, and it goes directly to one of the terminals on the solenoid valve, and I'll show a picture of that here in a minute. And then for the positive power to the solenoid valve, we have this red wire you can see here is run from the positive 24 volts on the power supply up to the center terminal on the relay, and then from the top terminal on the relay, that 24 volts is passed back down to the solenoid valve. So basically this relay just turns the 24 volts, the positive 24 volts, on and off to this solenoid valve. So if we look at the manual on, I believe, page 255, I have some notes here on robot grippers that cover some of this. And you can see this is the red wire and the black wire. This red wire is coming from the relay to the solenoid valve, and this black wire goes to the ground on the 24-volt power supply. And what I wanted to point out here is this flyover diode. A lot of times when these solenoid valves actuate, they open and close, they create some noise interference that can disrupt your Arduino and the Teensy's serial connections and actually shut them off. So this flyover diode that's installed here helps keep that, eliminates that noise that happens. So I've got some notes here on the flyover diode, and then there's a link in the manual to some more information on a flyover diode and installing that. So now let's talk about the 5-way solenoid valve itself. These valves are fairly low cost. Here's an example of one that you can get on Amazon for $17. It comes with some quick disconnects and some mufflers to keep it quiet. These are the mufflers right here, these gold things. These are available in different voltages, 12, 24, 110. I'm using 24 obviously because we have a 24 volt power supply in our enclosure, but you can use any power supply that you want to supply to the to the relay. It doesn't have to be the 24 volts, and then you can select your port size there. The plumbing to the valve, it's called a 5-way valve because when the gripper opens or closes, air is going to be sent out to one side, and then when the valve is opening or closing, it's also exhausting air back out the other side, so that air has to exhaust out one of these two ports here, and that's what those mufflers are for. I don't have any right now, but you'll hear in a minute. This is pretty loud when the gripper opens and closes if you don't have the mufflers installed. But the top two ports here, these two ports are the two that will be plumbed to the gripper, and then these bottom two ports are where the air exhausts out, and that's where the mufflers would go to keep the noise down. And then of course they're just the output is just plumbed directly to the gripper itself. This gripper is an SMC gripper. This is the gripper that the robot's joint 6 tool adapter is designed for. This whole pattern is designed for this SMC gripper, but you can use any pneumatic gripper you want. You can drill and tap new holes in this as you see fit, or you could make a 3D printed adapter to put on there, but you can put any gripper you want on this pad. You don't have to use only this gripper right here. So now with the pneumatics all hooked up to the solenoid valve and the solenoid valve wired to our relay, we can now control our gripper. Obviously I just have it sitting here on the table for this video, but you would have this on your robot, and you would have these air lines routed all the way up through the base of your robot, and you can mount the valve wherever you want away from the robot. So we can go to the input outputs page, and here we have a DO on and a DO off, and I've entered in the number 8 because we're using output number 8, which is the first one available to us. And you can see when I hit on, the gripper closes. When I hit off, the gripper opens. And you can hear that's pretty loud because I don't have mufflers plugged in there, but the mufflers will help keep that sound down. And then from the software, if you want to control the gripper, you would come in here into the software, and I've just got a test program here, and you can come in here to the set output on, and I'm going to put in a number 8 for output number 8 and set output off. And so I will go here into my program and I will set the output on, and then I could add some motion or whatever I wanted, and then I could set the output off. So now when I execute these lines, when I execute on, the gripper closes, and when I execute the line off, the gripper opens. So that's all of the information for the pneumatic gripper. Next I wanted to talk about servo grippers. I have an example set up here with a servo gripper that I purchased online. Servo grippers are available in a number of different voltages. Typically they're 5 volts, but they can be up to 10 or more volts. This particular gripper I have here is a 10 volt servo gripper. This gripper has a plug that has a black, a red, and a white wire. Servos can come in a few different color schemes. This particular one is black, red, and white. So the black is ground, the red is power, and the white is the control signal. A lot of times you will see ones that are brown, red, and orange. The brown is ground, the red is power, and the orange is the control signal. And some of the other ones, the high-tech models, the ground is black, the red or brown is power, and the yellow or white is the control signal. So In this case here, I have a black, a red, and a white. And then you can see over here I have a couple alligator clips that are connected to a 10-volt power supply. So I have 10 volts coming on the red and the black wire. So you know, depending on what the voltage is for your gripper, if it's something over 5 volts, you will need a power supply. If it's 5 volts, if it's a 5-volt gripper, you could power it directly from the Arduino Nano, and I'll go over that in a few minutes. But right now, with this 10-volt gripper, we have 10 volts right here. The red wire from the gripper goes directly to the positive power supply of the 10 volts. The black wire from the servo goes to the negative or ground of the 10-volt power supply, but the Arduino Nano's ground needs to be shared. It needs to be a shared ground. So you can see I have a ground wire connected from the Nano over to the black alligator clip, so that the servo and the Arduino are sharing a ground with the power supply. And then our signal wire, our white wire, I have that connected to analog input 0 on the sketch for the Arduino Nano. I've allocated the analog pins 0 through 7 for our 8 different channels that we could use. So I'm just using the first one. I just have that connected to analog 0. So that's how I have this gripper wired right now. And if we look at the software, in the control software, we have this function for servo. So I'm going to put servo 0 since we're on channel 0. And typically your servos will go from 180 degrees to 0 degrees. So I'm going to first add that command. So now I've got servo number 0 to position 180. And then I'm also going to add servo 0 to position 0. And I'll add that to my program. And then I'll bring the video back down here. So now when I execute this first line, the gripper closes. When I execute the second line, the gripper opens. So we can just basically control the position of our servo like that. And if you needed to, you can also, with a servo, you could control the servo to be, halfway open to an intermediate position. For example, I could do servo 0 to, let's say, 90 degrees, and we'll add that to our program. And if we execute that position, the gripper opens halfway. So you can control a servo gripper. That's kind of the cool thing about using a servo gripper, is it's not just open or close. You can control any position, and it doesn't necessarily have to be a gripper. It could be any type of an actuator. So now in this example, I just have a 5-volt servo. This isn't attached to a gripper, obviously, but it was just a 5-volt servo that I had laying around. This one has the brown, red, and orange color scheme on the plug. So I have the brown wire connected to the ground on the Arduino Nano. I have the red wire connected to the 5-volt terminal on the Arduino Nano. And then the orange wire, the signal wire, I have the orange wire connected to the analog pin 0 on the Nano, the same as the last example. We just don't have the 10-volt power supply in this case. And so you can see here I've got the same code, and if I execute the first line, the servo moves to the vertical position, and if I execute the 0 position, it moves 180 degrees from that position. So that just demonstrates hooking a 5-volt servo directly to the Nano, not using an external power supply. I also wanted to talk about inputs and how those are wired up to the Arduino board. You can see here I have a limit switch wired up to the Arduino Nano, and I have this limit switch wired up in the same fashion that the all the limit switches are wired on the robot, and that is 3 wires from the switch. So the red and the black wires. I have the red wire going to a positive 5 volt terminal on the board right here. The top left terminal is positive 5 volts, and that is going to the normally open contact on the switch that's labeled NO. And then the black wire is the ground, and it is wired to the normally closed, or the terminal on the switch that is labeled NC. And then I have a gray wire here wired from input number 2 on the Arduino Nano, and that is wired to the common terminal on the switch, or the one that's labeled COM. So the way this works is that when the switch is open, like it is right now, when it is not made or not contacted, the switch is passing the ground signal from the normally closed contact through to the common and back to the Arduino. So right now this Arduino input 2 is receiving a ground signal, so it is being pulled down to ground, and it is off. When I press and depress the switch, it's going to switch from sending a ground signal to the Arduino to sending a positive 5 volts. The switch is going to click over from ground to positive 5 volts, and it will send past the positive 5 volts through the gray wire to input 2, and then input 2 will be on. Now the reason we're pulling it to ground anytime it is not made is that microcontrollers and Arduinos are very susceptible to floating voltage, meaning that if you just wired a standard 2-wire switch, if you just had a regular 2-wire switch such as this one here that just has 2 wires, what would happen is it would not behave as you expect. You could the program would pick up, the Arduino would pick up floating voltage, and it would just kind of intermittently falsely detect positive and pick up floating voltage. So there's a lot of information online on that, on floating voltage, or you can look on the Arduino forums and look at stuff about pull up and pull down resistors. So you could use a 2-wire device. You just have to install a pull up or pull down resistor, and you can find a lot of information online about how to wire those up. But in this case, I just wanted to illustrate a basic 3-wire, the way that the robot is wired, to illustrate that. So in the program, in the software here, I have created a program here. I just called it test, and I've put in some comments, just some star comments in it, and that'll just let you see the cursor move. And then I have added an instruction called wait input on 2, and that is to create that line there. We have the right here, this button, wait input on. I put in 2, and I just click that button to put in wait input on. So when I hit play on that, you can see that the cursor just moves to that line and stops right there. Now this could be you know, you could wire up this input to any type of a button. It doesn't have to be a limit switch. It could be a push button or a start button. So if you wanted your robot to not start until you pressed a button, if you wanted, you know, a button to start your your program or whatever you're doing, you could put a wait input on at the very top of your program, press play, and then when you press this button, which I'll do now, when you press it, you can see the program will move on from that point. So that's a good way to to have a start button for your robot. Now the other one of the other functions I wanted to show was the if on jump functionality. So I have another program that I've created here as an example. So in this program, we start at the top. I have tab number 1, and then it's going to go down and it's going to evaluate this function, if on jump. And it's going to say if input 2 is on, jump to tab 2, otherwise keep going. And it's going to hit this jump to tab 1, and it's going to come back up here, and it's just going to keep running in this loop. And every time it's going to evaluate if that switch is made or not. So, you know, these asterisks here are just comments that you can see the cursor move through that would represent where you might have some robot motion, where, you know, the robot might be doing something, and if this switch is made, you might want to jump down to this tab and do some different motion down in here. Otherwise, you would just do this motion and then jump back up. So I will show you that here. If I hit play on that, it's going to evaluate, and each time it hits it, it sees that the switch is off, so it continues on and jumps back up to tab number 1, and it just keeps running through this loop. Now as soon as I depress the switch, it's going to jump down here to tab 2 and start running this logic. So I'm going to do that now. I'll click the switch, and now you can see that with that switch made, it has jumped down and is running that logic here. You can also control the robot just by sending it simple serial commands. You could write your own software or use any software. Right here I've got a just a free program called Cool Terminal, and I can just paste in commands to the robot. For example, here's a command just to do a joint move, and then I could paste in a command to do a circle move. And I'll paste in a move to do a move in the Z direction. And if you go to the config setting tab here, I have a last command sent to controller window, so you can use that for reference. For example, if we were to do a joint move of the robot and then go to the last command sent, you can see it gives you the string that was sent, so it gives you something to work with here, so you can use these for examples on building your own command lines to send to the robot. To control the 7th and 8th axes is kind of the same as it was before. You can use live jogging. You can just press the button and it will jog as long as you're holding the button. You can also put it into incremental mode, and let's say that we wanted to move it in increments of 20 millimeters. We could have it in incremental mode, and then just each time you click the button, the axis will move in 20 millimeter increments, and that's the same for all 3 of those axes. And now as far as wiring these up and calibrating them, if we go to the config setting tab, I've added a 7th, 8th, and 9th axis section right here. And so what we have here is I can define the length of the axis. So I can put in my overall length. I can put in the millimeters per revolution of the motor that my axis, how I want to define its movement. In this case, I'm just using a ball screw, and so that is 4 millimeters per revolution. And then I just need to put in my drive steps. So I have my current drive at half steps, which is 400, basically 400 microsteps. And so once those are in there, you can hit save, and that'll save that to the Teensy board, and it will calibrate that axis. And then as far as the step direction pins that it's set up for, the 7th axis is still, I put some notes down here at the bottom telling you which step and direction pins each motor goes to. Axis 7 is still pins 12 and 13, just as it was before. If we look at the manual, in the section for the schematics, I've got a little drawing here that shows the optional 7th axis, and you can see that the direction pin and pulse pin, the step and direction pins, are wired to pins 12 and 13. That's how they've always been, and I've left it that way so that nothing changes for people who have already built the robot. Then for the 8th and the 9th axis, I had to move up to pins 32 and 33 for the 8th axis, and then pins 34 and 35 for the 9th axis. So that information's right here. So it's not in the manual as far as that. It's not shown here in the manual, but it is right there in the software, so you know which pins to hook it up to. Another thing that we've added in this version is the ability to calibrate the tracks. As you know, with the robot calibration section is right here, and you can, as I've shown in previous videos, you can auto calibrate the robot. The robot will drive to each of its limit switches and calibrate each axis. So I've added that ability for the 7th, 8th, and 9th axis that wasn't there before. We can now install a limit switch on the track, and you can see here I've installed a limit switch at the end of my track, and then I can just click this button here for auto calibrate axis 7, and what that'll do is it will drive the robot to that limit switch, and it will calibrate the track to 0 just as it does for the robot itself. So now that it's done, it says joint 7 calibrated successfully, and if I come back to the main tab, you can see it's driven to its calibration point, and the 7th axis value is right back at 0 again. And then as far as wiring on that, we have, I've also put in these notes which pin to wire your limit switch to. So for the 7th axis, it's pin 36. For the 8th axis, it's pin 37. And for the 9th axis, it's pin 38. So as you can see here, let me open the manual. So in the manual, on approximately page 72, it goes over some details on wiring the limit switches for the robot. And so for the travel track or external axes or anything, for axis 7, 8, and 9, if you want to install a limit switch on them to calibrate them or to zero them, you wire your limit switch exactly the same way as you would for the robot arm. So right here you can see that the two normally open, normally closed contacts on the switch. I'm going to wire 3.3 volts from the teensy to this terminal, and then on this terminal here I'm going to wire that to the 0 volt or the ground terminal on my teensy board, and then this terminal on the limit switch, my common terminal, is going to go to the switch or to the terminal on the teensy board that's specified in the software. So if we look at the software, that's going to be that that terminal is either going to go to pin 36 for the 7th axis, or pin 37 for the 8th axis, or pin 38 for the 9th axis. So basically you just wire the switches up the exact same way you have for the robot, and just follow these numbers here for which pins to wire them up to. Now, you don't have to have a limit switch if you don't want to use the auto calibrate. You can also just run it to a hard stop or run it to a known position, and then just click on set axis to 0. So for example, if I was to jog my 7th axis, and I just jogged it an incremental to 20 millimeters, but let's say, for example, I powered off that drive and rotated the motor shaft manually back to a 0 position, I can just come in here to the config settings and hit set axis 7 calibration to 0, and it shows here that the 7th axis has been forced to 0, and you can see here we're back to 0 on the value for our 7th axis. And then lastly, one other thing to take note of. On the config settings, I did add a 7th, 8th, and 9th offset to the calibration offsets. And what this does is if your limit switch, isn't exactly where you wanted it, or it's not calibrating to the exact position you want it to, you can put in an offset here. So for example, let's say I wanted my axis to be 5 millimeters further forward when it hits the switch. I didn't want it to be at 0 when it's on the switch. I want it to be at 5 millimeters. I could put 5 in there, hit save, and then hit auto calibrate axis 7, and it's going to go through the calibration process, run the travel track up against the switch. It'll say calibrated successfully, but then if we look at its known value, it's going to offset it and start it at that 5 millimeter value that I put in my offset, and I could put in a negative value, or anything that I needed to offset it, but in most cases probably just leave that at 0. So now, as far as utilizing the 7th, 8th, and 9th axes as part of a program, or being able to play those positions back, these positions are all piggybacked onto the robot positions, and those are added as part of either a joint move, an offset move, a linear move, or an absolute rotation of joints move, a move R. So each of these move types, a joint move is just a movement using all joints defined in the XYZ yaw, pitch, and roll. Offset is an offset of a joint move, just offset by a position register in the registers tab. And then a move L is just a linear move defined in XYZ up, pitch, and roll, but it uses the kinematics to make sure that the robot arm moves in a perfectly straight line. And then a move R is just a movement that's very similar to a move J. It's just defined in the joint rotation value rather than the Cartesian XYZ value. But nonetheless, they all give you a way to utilize the external axes. So for example, if I click on move J and teach new position, you can see here that it has the robot positions, which currently I have the robot in kind of a home or an L configuration right now. And then joint 7 is recorded at 0, joint 8 is at 0, and joint 9 is at 0, which is where they're currently at. Now, if I were to, for example, I'm in incremental mode, 10 millimeters, let's move axis 7 to 10, let's move the 8th axis to 20 millimeters, and we'll move the 9th axis to 30 millimeters. And now if I teach position on that, you can see here that joint 7's at 10, joint 8's at 20, and joint 9's at 30. So basically, I didn't move the robot at all, but if I had, it would include that as well. So this could include a robot movement along with external axis movement, all coordinated together. Or if I want, I can just move, only what I change is added to the movement. So if I was to execute that first move, and now you can see all my axes are back to 0 where I taught that move, or if I execute the second move, you can see that all my axes move to 10, 20, and 30. So these moves can be either just the external axes, or they can be the robot only, or the robot plus one or two of them, whatever you want. So anything you put in here is what, is going to be played back. And it's the same thing for any of these. If I chose a move R in top position, it puts in a move R, and the same thing. The joint, they're all defined in joint rotations, but joint 7, 8, and 9 are just piggybacked on there. So we can basically get a signal from any type of a device that communicates over a COM port. In this case, I'm using this barcode scanner. I got this on Amazon. I think I paid $36 for it. It's a Terra brand device, and almost all of these barcode scanners can function as in keyboard mode or in USB COM mode. So if I open up the manual here to page 8, you can see there's a code here that I can scan, and that will put the device into USB COM mode. So now when I take the dongle from that device and plug it into my computer, it's when I open up my device manager, I can see that under my COM ports that I have a new COM port that just popped up, which is COM 6. So I know that this device is on COM 6. So now that we have the device configured and plugged into the computer to test it, you can go to the config setting tab, and there's a section here for testing the COM device. So this particular device is on COM port 6. And then I have this product box here that has a 9-digit product code. So I know that I'm looking to read 9 characters on this. So then I can press the test COM device button, and then when I scan the code, you can see that it puts the value in here. So we've got a 114-20289 as our product code here. So now we can accurately read in barcodes. So now to put this into a program, we'll go back to our main controls tab. And the first thing we need to do in our program at the top of the program is we want to use the functionality to read from that COM device. So in here, we're going to put in COM 6, and we're going to put in the 9 characters that we're looking for. And then we'll enter that into the code. So when it hits this line of code, it's going to read the value and bring it into memory. And it will place it down here in the manual program entry field. And it will also put it back on the same field in the test field that you saw earlier. The next thing we would want to do is decide what we want to do with a part if that code is scanned. So I'm going to come down here below the moves here, and we're going to select if COM device, and then we're going to say if COM device 6 is equal to, and I'm going to come grab this value, and I'll do Control-C to copy it, and come back here and do a Control-V and paste that code in there. You don't see all the characters, it's shortened up a little bit there, and then we'll call a program. So we need to create a couple of different programs maybe. So let's create a new program, and I'm just going to call it bin1, so that maybe we want to place a product in bin 1. So now I've got a new program called bin 1, and then maybe we'll create another program called bin 2. So now we have a program called bin 2. Okay, so I brought the video back in for the robot so we can see what the robot is doing. Now let's say that in our bin 2 program, let's say that the bin 2 is over on the right side. So let's teach a position there, and then let's load up our bin 1 program again. And let's say our bin 1 is over on the left side. So we'll jog the robot over here, and then let's teach a position there. And then we'll reload our test program so we can test this out. So now let's come over here to our if-then statement, and we're going to put in, let's do bin number 2 if we could have the correct product code. And so I'm going to come here below my moves, and I'm going to insert that. And now just to illustrate the test, let's put in a dummy number here. Let's say we have another product that's 288 instead of 289. And if that's the case, let's put it in bin 1. So I'm going to come back up here, move my cursor up, and I'm going to put that command into it. So now if we press play on the program, it's going to come to that line of code to read the COM port. We'll scan our product. It'll run those 2 moves. And then you can see when it got to the appropriate statement for product code 0289, it picked the bin 2 program, and the robot moved over to the right. So you could use this this COM device input, and then use that also for jumping to another tab in the program. So for an example, I've downloaded this image I found online of a lion that I'm going to use for an example. This is just a JPEG, and I have it opened in Inkscape. So the first thing I need to do is resize it. So we'll change, up here we'll change from pixels to millimeters, and then we'll lock the ratio, and I'm going to do, for the width, I'm going to do 150 millimeters and resize it. And then the next thing I'm going to do is up here on path, I'm going to click on trace bitmap, and that will open up the trace bitmap. I haven't played with the settings too much. I've just left them at their default settings. And if I click on the picture and hit apply, it should trace the image. And then if we come here and click on the node tool, it should show you all of the nodes that it created around the perimeter of the image after the trace. So now I should be able to save it as an SVG file. So I'm just going to save that to my desktop. Now, after I've made that SVG file, I'm going to open up my web browser, and I'm using this web-based Gcode creator called JSCut. I'm sure you could probably use, multiple different Gcode generators, but this is the one I've been playing with. So I'm going to open SVG, I'm going to click local, and I'll go find the line SVG on my desktop. And so I'm going to change the units to millimeters, and the max cut depth I've just been doing 1 millimeter. I'm going to change the units here for the tool to millimeters. For the diameter, I've also just been using 1 millimeter. Again, pass depth of 1 millimeter. And then the speeds, I've just been leaving them where they're at for now, at least for what I've been doing with drawing on a dry erase pad. And then for the material, millimeters, thickness, again, since I'm just drawing on it, I just did 1 millimeter. For the clearance, I've been doing 20 millimeters, and then Gcode units, millimeters, and then I've been clicking this button for return to 0 at end. So that should be, those are most of the settings I've been using, at least just for this example. And we can click on create operation, and you can choose either engrave and either engrave or outside. You can see when you click outside, it traces the outside of the SVG image, and then if you hit generate, you can see it turns to yellow, and it generates a Gcode file. So once that Gcode file has been generated, you can click save Gcode, and then I'll just save that to my desktop as lion.gcode, and then click local file, and it will save that to my desktop. So now that we have that Gcode file created, we can open up the AR4 software and go to the Gcode tab. So if you recall from the last video when I first released the Mark II, there was a little bit more basic functionality here and it was a little bit slow. These Gcode files are pretty big. There's thousands of little tiny moves for each arc and curve. I think this lion file is over 5,900 lines of code in that Gcode file. So what you'll need to do is insert a micro SD card in the Teensy 4.1 board, as you can see here. And what we're going to do is I've created the means to convert and upload each Gcode file to the SD card, and then we can play it directly from the SD card, so that there's no latency between sending all the moves back and forth. Just the files on the SD card, and it can play it directly, and it can play it pretty quick. So if we click read files from SD, it'll access the SD card on the Teensy and display here what files that I have on there, and you can see I've got a couple of files on that card already. And then what we'll want to do is jog the robot to a start position. This will just be above the origin of where the corner of the lion picture will be. So I've jogged the robot to a position above the board there and clicked set start position, and then I've put in an offset. This is a start offset, so this is 20 millimeters above this position, and I can click move to a start offset and move the robot to the position you see here on the screen. And then I can go ahead and load the Gcode program. So I'm going to click load, go to my desktop, find the Lion Gcode program and open that, and it's going to open up the Gcode program, and then we can give it a file name. I'm just going to call it Lion again, and we will hit convert and upload to SD. So that took a few minutes to upload and convert every single line to a line of robot code, but it's all uploaded to the SD card now. We can now click read files from SD, and you can see now there's a Lion program on there, and we can press the play Gcode file to start that file running. You can also play a Gcode file directly from the program command window. So, for example, I'll create a new program. We'll call it test. Click OK. So now we have a new program called test. I could, have some movements or, whatever I'm doing here, teach a couple positions or whatever. And then if we want to, type in the name of the file and click play Gcode, it'll put in a line, to play that file. The other thing, if you want, you can just go to the Gcode tab and click read files from SD, and then click on a program. If I wanted to run this punisher.txt, I could click on that, and I come back here, and it's already it populates that window for me, and I can click that button, and it puts in a line of code to run that program. So when you come up here and hit play, it'll run through any code you have, and when it comes to this program, it will run that Gcode program that you uploaded, which includes moving to this start position offset firstly, and then running the Gcode program based off of this position. That was one thing I didn't mention earlier, is that you have to set a start position. The Gcode file has just the basic movements from an origin of 0, 0 on the XY, so all of those movements for that entire Gcode file are based off of this as your start position. And so when you start the software, it should pick up all the cameras on your system, and you can select the camera you want to use. Select Start Camera. That'll turn the camera on. This screen over here on the right gives you a live view of what the robot sees, or what the camera sees. The robot needs to be at the top of your picture. The orientation, the way you orient the camera is important. The robot needs to be at the top, and when the robot moves in the X direction, it should be moving in this way that I'm moving the mouse, and then it should be in the Y direction, should be moving this direction, and I have that also shown up here on the border of our workspace. So I can click Snap Image, and that will grab a black and white screen grab from the camera. That's not a live view. That's just a screen grab one at a time. So the first thing we want to do is zoom in on our workspace. We want the wherever we want the pick area to be to kind of fill up the majority of the area. So I'm just going to zoom in a little bit there. So that's we'll go a little bit more. So that's pretty good right there. And now the next thing we want to do is to start working through the calibration. So we're going to calibrate pixels to millimeters, and to do that, in the software folder, there's a vision grid you can print out. It can be any size. I'm going to put the vision grid over my pick area, as you can see here. Now it's important that on this vision grid that the X1, Y1, the Y2 and the X2 position, that those fall over the backdrop, the color. You can see here I've got a conveyor that's black with silver on the edges. I don't want any of those dots to fall on the silver areas, and the reason is when we teach these pixel positions serve two purposes. One, for the calibration, but also for our background color, because when we go to mask out everything we don't want to see, it's going to grab those positions, those pixel positions, and grab the color there to choose our masking color. So I will hit Snap Image there to bring up a new screen grab. And all I have to do is, you can see right now that all these values are 0. If I come over here and I bring my mouse and I center it right over X1, Y1 and I left click, it'll automatically grab those pixels and put them into those fields for me. And then I will go to X2 and click, and it will grab that value and put that in the X2 field, and then I will click here on the Y2 value and it will put that in the Y2 field for me. So now I have all of my pixel positions taught. The next thing I want to do is put a pointer in the robot gripper. So you can see here I've got a little 3D printed pointer, and this part file, you can find this in the miscellaneous print files under the downloads. So with the pointer installed in my robot gripper, I have jogged the robot over the X1Y position. As you can see here, I have the pointer tip right over that dot on my calibration grid. So we'll go back to the main controls tab, and we'll look at our values here for our X and our Y. Something to keep in mind, I have the gripper perfectly straight up and down. So, you'll want the RY to be close to 180 and your RZ and your RX close to 0, just to indicate that the pointer is vertically straight up and down over the target. So you can see here we're at about 325 in the X and negative 276 in the Y. So we'll go back to our Vision tab, and for the X1 position, we will put in 325. And for the Y1 position, we will put in negative 276. So now I have jogged my robot over the X2 position, so the pointer is directly centered over the X2 dot, and our value in the X is 499. So I'll come back here to the vision, and for the X2 position I'm going to put in 499. And now I've jogged my robot to the Y2 position and have the pointer over the Y2 dot, and we can see that our Y value is at -93. So I'll come back to the vision and put in -93, and we can click save on that. And so now our calibration is saved, and our pixel to millimeter conversion calibration is complete. So I've jogged the robot out of the way, and we're done with the calibration grid, so I can remove that now. The next thing is to work on the to set the contrast and brightness. And one thing I wanted to mention was lighting. It's important to have really good even lighting over the top of your work area with as few shadows as possible. You can see here I've got a couple shadows which are not ideal, but I'm using a ring light over my camera, which I think seems to work the best. So I highly recommend doing the best you can to get as even lighting as possible. It's very important. So the next thing to do is I'm going to put an object in the field of view that is going to be my target object, just to help me identify the contrast. So I can snap an image over that, and we want the background to have as few shadows as possible and to be as even as possible. So I'm going to adjust the contrast until I start to get a really dark background, and we'll reduce the brightness. So now we've got a really good contrast between our piece. The background looks nice and dark, and we can now, once we have that where we want it, again we can hit save to save that, and then when you open and close the program, all these settings are saved: your zoom, your brightness, your contrast, all your calibration values. So every step I save where I'm at. And then the next thing is the mask. To mask the areas that we're not looking at. We don't want the vision to get any erroneous finds from finding other shapes or pixels around the exterior. So what we can do is just create a box around our pick zone where we want to pick, and what that does is that it will just save that area as our pick area, and it'll mask out everything else. And it will use, like I mentioned earlier, it'll take this X1, Y1, X2, Y2, all of these positions. It'll take each of those positions that we taught, and it will automatically grab those as our background color to mask this out. Now, if you have trouble with that and it's not working, you can unclick the auto, and you can enter in any value you want there. So, for example, if I were to, if my background was a different color, let me do a screen grab of that and then open up Paint, and I'll paste in a screen grab of that. And then if I use the color picker and I pick a color, you can see that I've picked black, and that is 000. If my background was white, it would be 255, 255, 255. Or, if I pick like here the floor, you can see that's 99, 97, 73. It's black and white, so all three numbers are going to be the same for a black and white image. The conveyor, for example, is about 84 without the contrast and brightness setting. So if you had a little bit of a grayish background that was 84, you could come in here and put 84, 84, 84 in here. The auto seems to work pretty well, but I just wanted everybody to have the ability to manually set the background color if you need to, if you want to, but I'm just going to leave that on auto. So now that we have our calibration done, we've got all of our brightness and contrast and everything set, we can actually teach an object. I want to get the object as straight as possible. So that looks pretty good. And we can click Teach Object, and we can draw a box around it. I've had the best luck making the box fairly good size around the part so that I capture a good amount of the background color around it. If any shadows are cast, or if there's any lines on your conveyor belt or anything like that, I've had better luck having more background color than less. So I will save this. It's a keystone jack, so I'll just call it jack and hit OK. And so now all of the parts that I've taught should show up in this list, so I can select jack and it will show me what I'm looking for. And then when I hit snap and find, it will put crosshairs over it. And you can see on these crosshairs there's a little dash at the end to show you which direction is 0. So now when I move the object around and click snap and find, it finds it, no matter where we put it in the field of view. So the score threshold, if you're trying to find similar parts and it's finding the wrong part, we have a score threshold that can help you filter out finding the correct part. So what I typically do is just take the object out of the field of view, and you can see here's the found scored value. So if I do a snap and find and it's not in the field, it can't find it. If it can't find anything above our score threshold, right now it's set to 65. Right now it thinks that it found the object at a score of 50. So what it's looking at is it found enough of this black background to think that it found it somewhere in here. So I'll just do several snap and finds and just kind of see where the minimum value is. And it seems like 51 is the highest I've seen, 52. So it looks like 52, let's call it 55. So if I put in a score threshold of 55, that should be a pretty good value. That should be, that value is going to be as low as we want to go to find the part. So now when I put the part back in the field of view, it found it at 99. So that's just a way of trying to figure out where our minimum score threshold is. Usually somewhere 70 to 80 is probably best, but just showing you there what you can do to find the minimum score threshold. So a couple of the other settings here. We have this full rotation search. That was something I was using for some initial testing, and it might come in handy for for doing some testing and setup. But basically, currently I have an algorithm written that does kind of a smart search that splits the difference in the angles and searches fairly quickly and should be able to find the angle within 15 tries. This full rotation search will search every single angle all the way around, so it's a lot slower and not always as accurate. So I don't really think anybody will need to use the full rotation search. The pick closest 180, what that is reduces the robot's rotation. So if you have a part, you have a parallel gripper, and you don't necessarily need to pick the part at specifically at 180 degrees. You can leave this checked, and I would suggest leaving that checked if you can. I guess to better explain that, I've got these plier jaws I'll try and use to simulate a gripper. But this part, I could either grip it this way, or the robot could flip around and grip it this way. If the part is specific and you need to grip it a certain way, if it has to be gripped with, say, the north end of the gripper towards the shallow end of the plug, then you would want to deselect pick closest 180 and unselect that. So let's say that my part is rotated to, let's say, 135 degrees. Now, if I have pick closest 180 off, the gripper is going to rotate a full 135 degrees to pick it so that the north end of the gripper is at the tip of our part. Now, if I have closest 180 on, basically what it's saying is it doesn't really care if the gripper picks it this way or if the gripper picks it this way. It's a mirrored part, so it doesn't matter. So with this selected, instead of moving 135 degrees in that direction, it's going to go the shorter distance and only go 45 in this way to pick the part. So that's what closest 180 does. Now if I have that deselected, keep in mind that due to the limit switch on axis 6 to be able to have the auto calibration, the rotation of axis 6 is limited to 155 degrees in either direction. So the pick angle, when this returns a found angle and the robot comes to pick it up, all of that rotation is a tool offset. It's based on the rotation of axis 6. So if I have this pick closest 180 off and the robot and my part is beyond, let's say it's like 170 or 175, the furthest that axis 6 can go is 155. It won't be able to get there. So if you have pick closest 180 off and it's beyond the robot's capability, it's not going to find it. It's going to give you that the part wasn't found. So then you can also select try closest when out of range, and what that'll do is the robot will go to 155 degrees and it'll be a little bit off, but maybe it can still get it. So that gives you a chance to still grab it if it's out of the rotation range for the robot. Now down the road I may see if I can set up an option to remove the limit switch and let you manually calibrate axis 6 to get a full 180 in both directions, which would probably be ideal. That's not in there yet, but that might be a future feature. But I've had the best results when I can pick the part either way with my gripper and leave closest 180 on. So now let's get into creating a robot program to pick the parts. I'm going to go to the main controls tab, and I've created a program called Vision Example, just a blank program. So at the top of my program, I want to turn the camera on. That will turn on whichever camera is selected. And when you save vision data, each time the program opens, it will default back to the saved camera. So it'll always open this camera, and your program will turn on that camera. There's basically two things we need to do. We need to find the part, and then we need to pick the part. And along with picking it, we'll place it or do something with it. So here at the top, tab number 1, I'm going to hit Get Selected. I'm going to change that to tab number 0 and replace that. And then I'm just going to put in a comment that this section of code is to find part. So I'll put that right here. So tab number 0 is where we're going to find the part. And just for readability, I'm going to insert a few blank lines. And then we're going to find two parts actually. So I'm going to, so we're going to call this section Pick Part 1 and insert that. And then we need Pick Part 2, insert that. And then I'll just insert a few blank lines in between there. So under Find Part, under tab number 0, the first thing I want to do is move my robot to an approach position. And I have the robot right now jog to a position right in front of the conveyor. So I'm on move J, and I'll just hit each position. So that's my approach. If I want to, I can hit Get Selected, and I can overwrite this star with the word approach so that I know that that's my approach move. And then what I'll want to do is do a vision find for our first part. And so what we have here under the vision find function is if it finds it and passes, we want to go to a tab that's going to go pick the part. If we fail, we want to go back to the top and try it again. So let's see here. So for pick part number 1, I'm going to create a tab number 1, and I'll put that there. And then for pick part number 2, we'll create tab number 2, put a tab there. So we have a place to jump to for our first part, and we have a place to jump to for our second part. So up here under the vision find, if it passes for our first part, we want to go to tab number 1. If it fails, we want to jump to the top at tab 0. So I'm just going to click that, and what that's going to do is it's going to go grab, in this line of code, you can see it says jack.jpg. So because I have jack currently selected, that's what it's going to put in the line of code. I can, of course, I can grab that line. I can grab that line and edit it and reinsert it if I want to. But I put in its background color set to auto. Its score is currently 55, and then if it passes, it's going to jump to tab 1. If it fails, it's going to jump to tab 0. So now the next thing we're going to do is for part number 1, we want to go pick the part. So from this drop down, I can come down here and select Move Viz, and then on tab number 1, I can select Teach Position. Now before I do that though, what I want to do, so here on the Vision tab, we'll want to place our object in the field of view, and we want to put the object straight up and down so that when we hit Snap and Find, that the found angle, we want to make sure that that found angle is at 0 degrees, because every pick from here on out, when it goes to pick the part, it's going to be based on a pick position that's taught at 0 and a part at 0. So we need to make sure that the pick is taught at 0 degrees. So now you can see I've jogged the robot over the part. I've centered the gripper over the part and set it at a good height to pick the part. So now that I have the robot in a good position, I can come back to the main controls tab, go under tab number 1 where we're going to jump to when we pick that keystone jack, and I can hit Teach New Position for Move Viz. So one thing to keep in mind, that all of the Move Viz is always offset by position register 1, and the reason for offsetting it by position register 1 is to allow us to offset to approach above the part and then come down to the part to pick it. So I'll show you that here in a second. It puts in the current X and Y value for where the robot is right now, but those don't mean anything. When it actually goes to pick the part, the Move Viz function will throw those away. It'll throw away the X and Y, and it will replace them with the robot's X and Y position where it actually found the part, and then it will also offset it by that found angle right there. We also have the rotation, that it will use these rotations however you teach it. It'll use those rotations. So with the part at its 0 position in front of the camera, the gripper also needs to be at its 0 position over the part. And then of course you can set your track position, speed, acceleration, deceleration to any values that you need. And then I think I skipped over the height. It'll use the Z height for how high you pick the part. So that's the Move Viz. So now let's say that I want to actually move above the part. I don't actually want to move to it. So I'm going to come back here, and right before that Move Viz, I'm going to take position register number 1, and element 3 is the Z height. So if we go to registers, these are just position registers that store an X, Y, Z, yaw, pitch, and roll value. The third one in is the Z, and so what we want to do is offset that position in the Z by, let's say, 25 millimeters. So I'm going to insert that right there, and so now when I execute that line of code, when I come here to position registers, it sets the Z value to 25. So now when it actually executes this Move Viz, it's going to come 25 millimeters above the part. So now what I want to do is now that I'm above the part, I'm going to set it back to 0. So I'll set that position register back to 0, and then I'm going to hit Get Selected on that, insert it right there, and so now it will move. It'll set the position register to 25 millimeters high. It'll move 25 millimeters above the part. It'll set it back to 0. When I execute that move, it'll move right down over the part. So now the next thing I want to do is close my gripper. So I have output number 8 wired up to the solenoid valve that controls my pneumatic gripper. So I'm on the wrong line there. I want to set output 8 on. So that'll turn on my gripper, that'll grab the part, and then I'll want to move back up. So I'm going to, again, set my position register 1 back to 25 or any height that I want. So I'll hit get selected on that and insert that. I'll hit get selected on the move and insert that. So now I've gripped the part, I've set my position register back to 25 millimeters up, and now I've moved up above the part. And then now I can program a couple moves to move somewhere else. So I'm just going to from that position right there, I will just jog straight up in the Z, and I will teach a move J, and then I'm just going to move joint 1 over to the side for now and teach that position. And then right here is where I'm going to drop the part. So then I'm going to set output 8 off. And so now I've released the part, and now what I want to do is jump back up to the top to tab number 0 and move back to my safe approach and look again for a new part. So right here I'm just going to put jump to tab 0, and now it will jump to the top and repeat that process again. One other thing that I forgot here is that at the approach, before we go get the part, we want to make sure that we open the gripper. So I'm going to set output 8 off right up here near the approach. So now let's hit play on this. The camera's already on, so we'll just start the program right here and hit play. You can see here it's going to take a picture and find it, and the robot will go down 25 above, down to a picket, come up, and then bring it over and let it go. So we'll come back to the Vision tab, and you can see it's just flashing red. It's just looking for the part. It's looping through the program. So as soon as I put the part in the field of view, it will find it, and the robot will go get it. So I'm going to hit stop. And so now if we wanted to find a second part, so what I'm going to do here is I'm going to copy and paste everything from tab number 1 down into tab number 2. So now I've copied everything from tab number 1, everything to pick that part, down to tab number 2 to pick a second part. And then of course I can modify these positions to place the part in a different spot. But the thing we'll need to do now is to add a second visfind. This is for the jack part. So let's just let's hit get selected on that, and let's just insert it. And actually let's change jack. I have another part that's a plug, so I'm just going to change that to, let me take caps lock off there, change that to plug, and we will replace that line. So now I have one visfind for jack and one visfind for plug. Now for plug, if it passes, I want it to go to tab number 2 instead of tab number 1, so let's change that. So now we've got the plug. We're going to jump to tab number 2. The score, you may want to, be careful on your scores and make sure that your threshold is set correctly so that you avoid any issues. And so now the next thing we need to do is right above this visfind, I need to create a new tab. I'm going to do, we've already used tab 0, 1, and 2, so we'll just do tab 3 and create a tab right there. And so now on this first visfind, if it fails, I don't want it to jump back to 0 because it's just going to sit here in a loop and constantly look for the jack. It'll never look for the plug. So I want to get that one, and so if the jack fails, I want it to move down to tab number 3, and I want it to look for the plug. So I'll replace that line of code. So what it'll do is it'll look for the jack. If it doesn't find the jack, it'll jump to tab number 3, it'll look for the plug. If it does find the plug, it'll jump down to the section of code for picking the plug. And if it doesn't find the plug, it jumps back to the top and looks again for the jack again and just cycles through this. So this is how you would set up a program to find multiple different parts, and you could set this up for, you know, finding as many parts as you want. So one other thing here, this plug is a little bit shorter than the keystone jack. So I've gone in here into the pick position. Instead of picking at 0 on the plug or on the jack, we just set it to 0 to where our top position was. So if I want to just reuse this code without reteaching the position, I just, you know, copy pasted all this code, and then my pick position I can just adjust it. So I made it -10, so it comes down a little bit lower than picking the plug, or picking the keystone jack, excuse me, to pick the plug. And then the other thing was the score threshold. I had a little bit better luck setting these to 65. So now if I come up here to the top of the program and hit play, the program's just going to sit here and cycle through, and when I put the plug in place, it'll come in and find the plug. So it'll just continue searching there, and then so I can put the jack in the field of view, and then the program will find the jack and the robot can go grab that part. So that's the majority of teaching and picking apart, but I had one other topic I wanted to cover real quick. I wanted to come back to this pick closest 180 and try closest one out of range. So if you do need to pick the part in a particular orientation, and that axis 6 rotation of 155 degrees could become problematic, I would recommend teaching the part a little bit differently. Since the picking of the part, the found position is a rotation of axis 6 when it gives this angle, when it returns this angle. If you're trying to pick at a specific position, you might have better luck if you actually teach the pick with the part at the robot's axis 6 0 position. So basically what I'm going to do is I'm going to jog the robot down over the pick area, and I'm going to rotate axis 6 to 0. So I'll do that now. So now I've jogged the robot down over the workspace to a good pick position for the part, but I'm making sure that axis 6 is at 0 degrees. So you can see here with the robot in this position, the gripper isn't square to the conveyor because my robot base is not perfectly lined up with my conveyor, and that's kind of what I wanted to talk about here. So now if I jog the robot up and out of the way, so I placed a part in the jaws with the axis 6 at 0 degrees, and then jog the robot out of the way, and you can see the part is not straight up and down. That's how the part would sit with J6 at a perfect 0 degrees. So what I want to do in this case is I'm going to go ahead and teach the keystone jack while it's at that orientation, and I'll just call that Jack 2 and hit OK. And so now when I select Jack 2 and hit snap and find, that is going to be, even though the part's not sitting perfectly straight to the crosshairs, that is going to be the 0 position for the part. So the 0 position for the part will perfectly match the 0 rotation for J6. So now with the part taught like this, I'm going to have the best opportunity to rotate a full 150 degrees to the right or 155 degrees to the left and have a better chance for picking that part. So I just wanted to kind of cover that topic if you are needing to pick the part at an exact orientation. So that's everything I have for this tutorial. Shoot me an email if you have any questions, and thanks for watching. I've also added a new tab, this kinematics tab. This exposes all of the kinematics and settings for the robot. So if you have your own custom robot, you could come in here and put in your motor directions, your calibration directions, your position limits for your axes, and then gear ratios, drive micro steps, and then all your DH parameters. So you could use this to control any robot.